All right, question 5 is the SN2 inversions question. And this is a very important concept in building up larger molecules because, as I talked about before the exam, we don't always have access to enantiomer or starting materials. Sometimes we have access to only one of them, either access to it, only one is available, or one will be exponentially cheaper than the other. And, even if the government is paying for your research, it's still got to have a budget, and so you can't waste money. So having the ability to actually create stereoisomers from a single starting compound is a big deal. In this case, we have one stereoisomer, one stereocenter that's set, so these two products would be diastereomers of each other, which means we could actually separate them from a mixture if we had to. Not relevant to this question. Okay. The question that comes up is, one, what's happened to the stereochemistry by the time the process is over? Neither of these is one step. It actually is two steps for both of them. The question is how many inversions happen along the way. The SN2 reaction is our only control of stereochemistry, and it involves inversion every time. So if something looks like it's been the same, like the product for reaction A here has the same stereochemistry at that carbon, it means there have to have been two inversions, or potentially 4 or 6, but there have to be an even number of inversions. Generally, it's going to be 2. For the bottom case, where it appears to be the opposite, then there's an odd number of inversions. Generally, that's only going to be 1. So the question is, our nucleophile coming in is going to invert the center as our leaving group. So that means that the step before this, in both cases, I'm going to have the opposite stereochemistry leaving group. So I'm going to have my leaving group here, up in that case. And in the other, it's going to be down. The nucleophile is going to invert. So these are not going to be the same. So I'm going to just notate them 1 and 2. These are not identical leaving groups. So if I make an alkyl halide, a bromide, a chloride, that is an inversion of its own. That is an SN2 reaction. So that's going to give me an inverted leaving group. That would give me this one. So for instance, if I treat this with PBr3 or SOCl2, would also work the same way, what I'm going to get is an inversion of the alcohol carbon. So what I'm going to get is this. A leaving group that's pointed up. So this is an SN2 reaction. And then my nucleophile, strong nucleophile, is also an SN2 reaction. Those are my 2 inversions. In the bottom case, I don't have 2 inversions. I have 1. That is a prototype for making a sulfonate. So if I treat this with a sulfonic chloride, SO2Cl, and a base to mop it up with, what I'm going to get is this. I'm going to get a sulfonate like that. It's important to note here, I haven't touched this carbon to oxygen bond, which means I haven't changed the stereochemistry. Just the OH is a crappy leaving group. So I've either got to replace it with something like halogen, or I've got to attach something where the hydrogen was to make it much more electron withdrawing so that I can displace it, turn it into a proper leaving group. As an OH, it isn't one. The OH is a terrible leaving group. So now that I've done that, that's not an SN2 reaction. Nothing's happened to this carbon. Nothing. It is untouched. So now when I treat this with a nucleophile, I'm only doing 1 inversion, and I get this one. This is the product for part B. So both of these reactions are 2 steps, but not the same number of inversions. The leaving group can, in the case of A, or cannot, in the case of B, cause an inversion to make the leaving group. Then the nucleophile in an SN2 reaction is always going to be yet another inversion. So, now, part B of the question was which one would be more difficult from the leaving groups on the far right here. And that is a concept that we're going to come across in later chapters, and also if you went beyond the two courses of this sequence, you'd see it more often. And that is, we don't only have to worry about the site we're reacting at, we have to worry about its neighbors. So we have a problem here. My nucleophile is trying to come in opposite the leaving group. So in the upper case, that means it's coming in from here, below. Not really a problem. If I look at it as coming directly below the plane of that leaving group, it could, kind of be drawn this way too, up here. It doesn't really have any obstacles. But if I look at the other one, I've got to come in from above. This lower leaving group case, I've got to come in from above. That has something nearby. So there's an obstacle there. It's not a big obstacle. It's not on the carbon in question, so it's not like a T-butyl group that'll stop the reaction. But it's still there. It's still an obstacle. A small obstacle is energetically the difference between a reaction that works at room temperature and one that has to be heated up. On a small scale, that's trivial. On a large scale, that's a lot of money to heat a reaction up even a little bit. So the fact that this is a little harder to do doesn't mean it's impossible by any means, but it does mean it's probably going to take more work because there's a little bit of a harder pathway to get to that lower substitution pathway, to get that leaving group displaced by an SN2 in the lower example that leads to B is a little bit more difficult because of size. That methyl group is pointing in the direction of where the nucleophile has to come in. So it's going to be an annoyance. Probably not much more than an annoyance, but still, it's harder than the other case.